Okay, I request all of you to please gather as soon as possible so that we can start the next session. A very good afternoon, respected professors, dignitaries, participants, and my dear students. I welcome all of you in this session of International Conference on Applied Algorithms 2025, organized by Computer Science and Engineering and allied departments of Heritage Institute of Technology, Kolkata. Today, in the first half, we had heard a talk on oblivious algorithms and universal optimality by Professor Dr. Shondeep Sen. We have also seen the presentations of three papers from Track A, Discrete Algorithms. Now, we are extremely privileged to have Professor Dr. Bhargav B. Bhattacharya and Professor Dr. Partha Bhomik with us. I request the audience to give A big round of applause for them. Thank you, professors, for your presence. As per the schedule of this event, we will first have the talk titled How to Describe a Contour to Visually Challenged Perspectives from Computational and Digital Geometry by Dr. Bhargav B. Bhattacharya. This will be followed by the presentation of 4 papers from track B, Artificial Intelligence and Machine Learning. The session chair during this will be Dr. Parthabhumi. Dr. Parthabhumi did his graduation from IIT Kharagpur. He completed his master's and doctorate from Indian Statistical Institute, Kolkata. He is working as a professor in the Department of Computer Science and Engineering in IIT Kharagpur. Dr. Bhomik's primary research interest is digital geometry. He also loves working on applications in algorithmic art, combinatorial image analysis, computational topology, and computer graphics. His work has been published in numerous international journals and conferences, and he also holds 4 US patents. We are really honored to have you here, sir. I request Dr. Parthabhumi to please come up on the stage to chair the session. Over to you, sir.
It's a very rare privilege that I am on the dais to call Professor Bhattacharya for his keynote speech. And this is, as far as I know, possibly he is the senior most speaker of this particular conference among all the speakers and keynote speakers. So he has a diverse research experience. He has supervised around 15 scholars who are placed in different institutes like IIT, Icaa, even this institute, Yadupur University, IIST, so on. And this particular speech will be basically covering geometry in 2 different domains, one the discrete domain, another from the real domain. And I was fortunate enough to be his scholar. I have worked with him for quite a long time and still working. He is in the faculty of Icaa Kolkata, and he has visited number of foreign universities in US and Germany. And currently he is visiting Ashoka University. He also visited our institute, IIT Kharagpur. And we know him mostly not for his research experience or the research guidance he provides, but also for his kind of personality, like a saintly personality and very cool composer and very open-minded person who can follow you, who can direct you, who can listen to you, and then who can talk to you in your way. So that is his specialty, and that attracts many scholars, many collaborators towards him, and he has lots of collaborators in the country as well as abroad. So I will not waste much time on this. So it is better to listen to his speech right now.
Good afternoon, can you hear me? Okay, so in the afternoon session, half of the population is disappeared anyway. And after lunch, the remaining half will feel sleepy. So no, it's okay. There's a half-life of the conference session. Now, incidentally, Partha happens to be my PhD student, and with him I have written the maximum number of papers. So that's how with him I have written more than 60 papers. So I'm talking about digital geometry, and he is the expert in digital geometry in India. And here is Professor Subhash Nandi. He is an expert on computational geometry. Now, I retired many years ago. Right now, I am not doing any research. Anything, any talk you give nowadays should be charged with AI. So I am fortunate that I have retired before the invasion of AI. I have only one slide here, the last slide which I'm talking about AI. So the problem I'm going to talk about is how to describe a contour or a geometry, or how to teach geometry to the visually challenged people who cannot see. Okay, so this is a very, if you go to the blind school and look into how they teach, the basic geometry. If you cannot see the contours or the concept of straight lines or circles, how do you teach geometry there? So that's an interesting, very challenging issue to the educators, and to make it more inclusive. This is really still with the advent of many tools and many assistive tools, it is still a challenge. Okay, educating literature or other subjects is okay, but when you talk about which is diagram intensive like geometry or higher branches of mathematics, it is very difficult to communicate with visually challenged people. Okay. Okay, so this is just simple data. There's 285 people are visually challenged globally, and out of which 39 million people in India are completely blind. And so this is 30% of 30% of blind population, as you see, of the world population, and approximately 1% is completely blind in India. That is 1.4 crores. Now, so I'm talking about this problem from two perspectives. One from digital geometry, which essentially tries to represent some curves and contours in terms of pixels, where only in the discrete space, and also in the later part I will talk about in terms of the computational geometry. Okay, so for example, to visually challenged, how do you let them feel the concept of straight lines, circles, or polygons, or something like this, or even some contour? They cannot perceive. They cannot see. So no question of perceiving colors. Okay, but how about the contours, like the contour of diagrams or something like this, so they can have a feeling. So typically braille systems are used, but braille systems are mostly for to describe just alphabets and numbers and some punctuation symbols. That's it, nothing else. Okay, there is no way you can describe a contour or something like that. Now today some assistive technologies or tablets are available, but with some raised dots, so that they can feel. They can tactile dots, so you can feel them by touch to feel some kind of contour, but there are certain limitations. Okay. Okay, so how to address the unique challenges, to the educators face in teaching, for example, geometry to visually impaired individuals. So, and the shape recognition is an important task. Everybody should learn shape recognition in order to navigate to the real world and to compute daily tasks and so on. They must have some concepts of different kinds of shapes. Okay, so many years ago, maybe 35 years ago, I was teaching computer architecture in the University of Nebraska-Lincoln, and there was a student in my class who used to come in a wheelchair, but he was completely blind. Okay, as you know that teaching computer architecture requires a lot of block diagrams, and then a lot of logic diagrams and so on. Okay, and incidentally, during that time, technology was not that advanced. So that student has some kind of recording mechanism, and he has some special kind of tablets that time available for, and especially ordered for him from some companies. So he used to record my lectures, and then he has some kind of software which translates those speech to English language, and then automatically puts into braille. So 35 years ago, that technology was not available in public, but that guy has got some connection with some companies, and they specially manufactured for him. And in the university, there is a special cell so that they provide assistance to different kind of differently abled students. So they used to prepare all the class notes in braille and so that they can understand. So he used to come to me in office to get some clarification if he has some doubts and so on, and he performed very well. So so let us see that when I was teaching in the class, so this is the CPU block diagram, so everybody is, this is the basic block diagram of CPU. So as you see, so there is a box and there are some other boxes inside. So you see there is a contour which is a rectangle. Okay, so in braille that has to be described. And similarly, so something is written as a control unit, ALU, memory input output. So those legions can be translated into brailles, but the problem is with the contour. Okay, so how do we describe in terms of braille? So as you see, the braille is it looks like something like this. So there are some raised dots, and the students can feel it. And depending on the different kinds of patterns, each pattern is, corresponds to some alphabet. Okay, so they learn that alphabet, and when they touch it, there is a tactile feeling, and by touch, they actually learn to read different texts. Okay, so you see this Louis Braille, he was a French educator. He was partially blind. He invented this kind of script. As you see, there are 6 dots, and depending on, so there are 2 to the power 6 combinations. There are 64 possible combinations of raised dots, and using these dots, the alphabets and numbers are described. Okay, and in Braille there is no distinction between the capital letter and small letter. So it's a raised dot alphabets introduced in 1824, and it is still used nowadays. And this is the only way of the visually challenged people communicate, or the learning tool. Okay, so as you see that in Braille there are 6 dots, and the dots are raised or down. Okay, now today there are there are some kind of tablets available with grids. Okay, and because by virtue of program control, you can raise the dots and so on, so that the letters can be visualized there, can be felt there. So there are 6 dots, and they are numbered as 1, 2, 3, and 4, 5, 6. Okay, as for example, A is this. So this is on, and the rest is off. Okay, so B is this. So there is an alphabet like this, and similarly you have numbers. Now notice that the code for 1 and the code for A, they are same. Okay, so they are the same number. So if you want to represent a number, you need an additional prefix, and the prefix is this. So this is the numeric prefix, and so if you want to write 2 in Braille, so you take this symbol, which also the same as B, okay, and then you prefix this symbols with this. So now this becomes 2. So you first fill the first prefix, you know that this is numeric, and then they know it is 2. Okay, so to represent 2, you have to do this kind of thing. This is the Braille symbol for 2. Okay, so if you have a long number, you see that. Learning addition, multiplication in Braille is too complex, as you see. It's a lot of practice. And incidentally, although it was introduced more than 100 years ago, this is the technology still forward. No further improvement so far. No, if there is a big digit, say for example 100, you need 1 prefix, first 1 prefix, then 100. There is a gap, that's it. There are punctuation symbols, comma, semicolon, etc. Okay. And so there is a Braille typewriter like this. So what do you do? So suppose you want to type D. Now what is D? D is this, right? So it means that these 3 dots. So basically D means this one, and this one. So this will be quoted as 1, 4, 5. So you press here 1, you press 4 and 5. Then this Braille code will be printed there on paper with the raised dots. That's how you do it. And this is Braille typewriter.
So it is basically based on numbers, right?
Numbers means Right.
Like from ELW. So how can we type that?
Anyway, I mean, if you, any alphabet,
Yeah.
you know, for alphabet, so there is a code like this. Okay. And each code is an equivalent numeric like this, you know. So for example, D is 145. So you type 145 and the typewriter, you know, and there is an interface, mechanical interface, which actually prints this so that you can fill it. Well, okay, so I was curious, you know, how do they represent these block diagrams and complicated diagrams, logic gates and or in Braille's, you know. So I asked the student, you know, so he explained to me. So you see in Braille, the dash is this symbol. Okay, but there is no symbol for the vertical one, you know. There is a symbol for oblique dash, but there is no Braille symbol for the vertical dash. You know. Instead, there is a pound symbol which is this. Okay, so if you have a block diagram, okay, so now this is a sequence of dash, you know, in Braille. Okay, so instead of doing this Braille, you know, since this is dash, you know, you can do this dash so that you can feel it, you know, although it is not Braille. And similarly, you know, for vertical, you can do this kind of thing. Okay, and for the legions, whatever it is here, control unit. So this is in Braille. Control, this is unit, and this is input, and this is ALU. As you can see, that A is this. You see, only single dot here. So this is ALU, and this is output, and so on. That's how in Braille that is printed. You know, so he showed me this Braille printed sheets. You know, actually, you know, the Braille books are very, very thick. You know, in one page you cannot write too many things. And just few sentences, the paper page will be full. Huh? I'm not sure. I don't know. Somebody might be designed, but you have 6. But this is universally kind of thing. Of course, there are many conventions in English Braille, and you know there are certain variations in encoding. Well, so this says this block diagram of a CPU. So anyway, by virtue of tactile feeling, so they can at least have some appreciation, some, you know, concept. They can conceptualize what is going on here. Okay. So this was my other slide. So as you said, there is no problem here. There is a box here and some writing here. So in Braille, it's pretty straightforward. However, so when I talk about this slide, so now see you have a circle. Okay, so now in Braille script, what are you going to do? So that is the problem. How to describe this kind of contours in Braille? So that is really challenging. You know, how to do this? Okay, so how to express the circle in Braille script? So now, so this is so in geometry, when you talk about this, if you think of brails, you know, and you consider a series of dots. So now it becomes a grid of only dots, right? So this is essentially from an abstract point of view. This is the domain of what is called digital geometry, right? In which case only the lattice points are defined, not the continuous plane, right? So nowadays the tablets which are available for visually challenged people, so there are some kind of electromechanical device full of grids like pixels, and you can program them depending on the script. The corresponding Braille script will appear. They will go up. They will be pushed up, and they can be pushed up and down, so that you can feel you can read the script using by tactile feeling, by tactile scanning. So this is kind of. But still there are a lot of challenges, you know. The primary challenge is, you know, the scarcity of good programmable tactile devices and the lack of techniques that convey spatial relationship through touch only to visually challenged people. Notice that they can only get information through touch and through voice. So there is no visual cue, no visual input, only touch and voice. Okay, so so this is kind of modern bell devices. This is a programmable electromechanical silicon pad, and there are some some buttons inside it. You can push up and down. Okay, so for example, some I mean, you may say this is shown in English, but actually the symbols will be displayed there in braille. Because the visually challenged people, they do not understand this English or any language alphabet. They are not trained to learn them. Okay, they only understand this braille system. Okay, so the device is something like this, as you can see. So as you see, this is nothing but an array of pixels in the world of digital geometry, right? Okay. So suppose this is the set of this electromechanical patterns. Okay, and I want to all patterns should be embedded on this two-dimensional grid so that they can feel by finger, by touch, right? So if you want to represent a circle so that they can have a feel, that the circle would be can all be sampled through this grid points. Because only the grid points that is they are visible or they can feel only the grid points, right? There is no sort of continuity to a visually challenged person. Okay, so the visually challenged person will actually feel only this raised dots. So this is nothing but this is the discrete representation of a continuous circle. In other words, this is nothing but what you call in the domain of digital geometry is called a digital circle. Right, right, right. Yeah, but that's for literal numbers only.
Car or blue car or one. How am I going to act? Well, you can have alphabets like this.
You can have alphabets. Alphabets are different, the 6-digit code, the 6-dot code. But if you have shapes, that do not follow this 6-digit code. No, you can feel this. This is like a tablet. You can feel it. What are the raised dots? Circle is, what you can feel is this, not the circle. Okay, so the visually challenged person perceives the Euclidean circle not only in the Euclidean space, not in the Euclidean space, but in the digital space. Now, instead of square grid, you might have more dense grids like pixels, for example. In camera pixels, we have a dense grid, but in electromechanical device, that density is not practicable. Okay, so that high resolution is not possible here. So therefore, this deformation will be still there. Okay, so they perceive a digital circle. Notice that it looks differently from the Euclidean circle, of course. No, you just feel the entire plane. It's like imagine that you have a tablet, huh? You feel it, and then you see the contour. You see the raised dots, then you have feeling. You can look at you can follow the continuity. You just scan the neighborhood and feel in which direction the continuity goes. Okay. And so this I borrowed from Pastor's thesis, so he worked in digital geometry and the same thing, So this is the circle, and in the two-dimensional grid, these are the pixels which will be turned on. So in the discrete space, the digital circle has a different look. It's a collection of discrete points or discrete pixels, right? Okay. So now if I have a straight line, okay, the same thing. You will see this, right? So in the domain of digital geometry, this is called a digital straight line. So the visually challenged person will feel this one. Okay.
These are accidents how computer graphics work for the history.
Right. But in computer graphics, the problem, the advantage is you can have high resolution, you know, so that you cannot visually see this, you know. But in electromechanical device, that resolution is not practicable. So that error is still there.
Right, numbers.
Huh?
There was like one here.
You can write, but then in Braille you have to write, you know. And Braille has 6 components. One number requires.
And then I did one, two,
You know, 1, 2, 3, you can write, you can do it but in program, but visually challenged people, they are not trained to recognize those 1, 2, 3. They are trying to recognize only the braille alphabets and numerals.
See, they can be done on this.
You can do. Yes, sure. Braille can be done, yes. This is programmable. Braille can be done, yes. Yeah. You can do it. Yeah. If this is big enough, you know, I mean, there are 6 dots available. You can engage them. You can engage 6 dots here. They are very complicated. Yeah, not so easy. Okay. Now suppose you want to teach geometry to the blind, you know. Okay, to prove the sum of the internal angles of a triangle is pi. Okay, very fundamental theorem. Okay, so you draw on the touchpad, on the dot pad, this is a triangle you draw. Now what the blind people is going to visualize is this. This looks so weird, you know, how can you prove? There is no notion of angle comes in, right? It's very difficult to teach, even very fundamental, very simple theorem like this, not possible. Right? The concept of angle, you cannot simply disseminate to the visually challenged person using this kind of tools, this kind of assistive tools, not possible. Okay. So these are limitations. So because of limitations of the great resolution in tactile pads, you know. And so this kind of discrepancy always remains. Because in the digital space, you know, the contours are approximated. Okay. So basically now if you just relook into our knowledge of digital geometry, you see that a digital circle in the grid, they look like this, right? Or in the pixel space, it looks like this. Of course, some of the properties which are well known in digital geometry, so that makes confusing to the visually challenged world. You know. So, for example, in your tactile dot pad, the digital circle will appear like this, right? It will appear like this. Okay, so now if you want to teach them the notion of convexity, so an Euclidean circle is convex, but this is non-convex. Okay, so those properties, they are not directly translatable. Okay, so these are the problems of digital geometry, but they are reflected in the domain of visually challenged person. So digital straight lines are well studied by Rosenfield and other students. In fact, Professor Partha got a lot of, he did a lot of fundamental contribution in the area of digital straight lines. Okay, so they are characterized by a certain set of well-known set of digital geometric properties. And so if I am given this set of points, so they may not, it may not correspond to a digital straight line. So that means if this set of points are given, then this is not a straight line, something else. Okay, so they satisfy certain properties. These properties are not satisfied. Okay, so then there are other discrepancies, like say, for example, if you want to teach geometry to blinds, the two straight lines are either parallel or they intersect at a single point, right? But In the discrete space, this may not be true. Because in the discrete space, when you have a discrete line, so this will be represented by a set of grid points. And if you have another set of another line, so this will be represented by another set of grid points. Although the two lines intersect, but their digital set, they do not intersect. So the notion of intersection is not clear, it's confusing. All right. Okay, so in the Euclidean space, you have these curves and so on. So if you look into digital geometry, this is a very well studied area. And because of the lot of applications in image processing, computer graphics, and right now there have been good certain interest in braille education also, because they assist in shape perception and geometry education. All right. Now let us see how blinds are currently taught by how to draw figures and something like that. So here is a real life example. So this is how the blinds are being taught. To draw the drawing of a body, the contour of a body. So they give some statements like this, some instructions. Space 3 times, make period, make y, make 4 2 times, and so on. And then in braille they do this. So these are the braille symbols. And you see that this contour of the body. That's how the contour is represented in braille nowadays. So you give instructions in braille. What sort of braille characters you should put around the boundary so that it looks like a given contour, drawing the boundary. Okay. But with the advent of this dot pad and so on, you can translate the concept of digital geometry, With the advent of these instruments and these devices, possibly you can borrow some of the concepts from digital geometry. So for example, suppose you want to describe the map of India, the contour of map of India. So given this, so imagine that this is partitioned into smaller straight line segments, and then each straight line may be represented as a set of pixels. So you have some feeling in this. So this is a well-known techniques, in the area of digital geometry, that how to approximate the contour, and that can be mapped to in teaching visually challenged persons as well. With the advent of these new devices, these dot pad devices.
The shape of bird, right? People understand like reflect the bird and gets laterally inverted, rotated along the axis. It's still a bird or something.
I don't know. I mean, so these are just downloaded, so what are these? How do they teach drawing, You are filling it up, and the contour is described by this. So they have fixed what are the characters needed.
The big that we understand that it's the bird. Just the little.
Yeah, but they still have some feeling of the contour, because they are raised dots, Huh? They are raised dots. Interesting. And so there are many examples. Drawing a bird, drawing a temple, drawing a church. So they have some instructions in braille like this. Tactile perception is sharper, much sharper. Well, okay. So let us see some perspective from computational geometry now. Okay, so teaching geometry for the blind in digital space, to prove that internal angles of a triangle is pi. That's horrible, right? It looks weird. Yeah, because so this is how a triangle looks. It's horrible. You cannot prove that this angle is some of the internal angles is pi, right? Impossible. Okay, so let us look into the Euclidean space now. So this is the technique. You use matchsticks and coins. So what do? So to prove the sum of the internal angles is pi, so you use just matchsticks. so that they can have a feeling of a triangle, right? And then use two matchsticks, to figure out, to have them to pass the concept of angle pi by 2, and two matchsticks to again to so that they have a feeling of what is called the straight angle or pi. Okay, so they can feel it, So this is the triangle area. Some kind of triangle is there. Now put another matchstick is there, and they can then try to feel this separation here and separation here possibly equal, and then separation here and separation here possibly equal, and they have some understanding of this. This angle is same as this one. So in the matchstick space, it is much easier. So this is in the computational, in the Euclidean space, where teaching geometry is much easier, right? Due to visually challenged, but this is just an example. Okay, very interesting, simple techniques, right? Okay. Another example, so they can have a feeling of the polygon also. All right. Okay. How about this? Okay. So to visually challenged person, you want to just pass this notion that if you have similar circles, then the central circle will be surrounded by exactly six circles, Okay, so they can have a feeling with the circles, these coins, and they know that the coins are of equal size. And once they have this feeling, so they can have an understanding why exactly 6 similar coins are there. So use these matchsticks and coins to figure out, well, so basically there are a configuration like this which they can feel, okay, and they can put matchsticks like this of equal length so that they can have a feeling of a regular hexagon, okay, and then just feeling at the center here, they put other matchsticks to see that, and they are equilateral triangles. So now, if you have the notion of the 60-degree kind of thing, they will understand why there are exactly 6 of them surrounding the central one. So use of coin and matchsticks, just physical things to pass them to have some knowledge of geometry. This is good, pretty interesting. Okay. Not only that, so they can understand this. All the 6 circles around this, all the 6 triangles around this, and they are equilateral. So now, if we have some concept of 60-degree here, because they understand pi, 2 pi, pi is 180, and then 2 pi is 60 degree divided by 6, and so have some understanding of equilateral. Possibly could be done with much ease, okay, rather than the dot pads kind of thing in the digital domain. Okay. Not only that, you can also teach them algorithms. How? Suppose you have different sizes balls, different sizes balls, so they can feel the size of shape of the ball, which one is bigger and smaller, and you ask them to sort them out. So you ask them to sort the balls in the ascending order of the sizes. So they pick the biggest one, largest one, okay, and put the largest ball on the right side, and then they repeat the process on the remaining one. Again, picks the largest one and put it on this side and repeat this. Okay. So using these balls, you can teach them, bubble sorting. Right? So bubble sorting is done. So that's to visually challenge, you can teach. This is one of the basic algorithms how you should teach. So you just ask them to compare. So initially there is a random arrangement, and finally there are pockets where they have to arrange in sorted order. You compare one by one, you feel the size of the ball, and if this one is larger, you ask them to interchange. So in one pass of the bubble sort, the largest one will be on the right side, and repeat this. Algorithm is done. Okay, very simple technique. Well, okay, so last I want to talk about something here. So this is kind of how do I construct the polygons? So when you were a kid, you must have seen this kind of thing. Some points are given, you connect them in series, and some shapes. You reveal some shapes, connect the dot problem. A very simple thing. So if the points are given, you know that you have to connect them in sequence. And if you do that, okay, so some shapes will be visible. Now imagine that if they are visually challenged, then first of all, this 1, 2, 3 should be written in brackets, and moreover, they don't have any notion of this continuity. Okay, unless you have mastics or something like that. So that's not possible for the visually challenged person. Okay. Okay, so if you know these symbols, and for a normal person it is okay, given the levels you construct the polygon. What if? Okay, now first look into this. Suppose these levels are given and you are asked them to connect. Okay, so some polygons or shapes come in. Okay, but remember, given a set of points, level points, sometimes it may not be possible. So, for example, in case of, for visually challenged, so for 2, you have to write this numeral prefix and this breadcrumb. And then for swap, again, the continuity is a problem, as I mentioned. Okay, so now, sometimes even for regular persons like us, if some points are given labeled this way, and if you want to connect them, 3, 4, then polygon is not possible, intersecting, right? So there are many things which you have to take care of. Now, suppose these points are given 1, 2, 3. See, already looks jumbled up, right? Even if you can see it, constructing the polygon is not so easy, From 1 you have to go to 2, then 3 is here, then 3 to 4, 4 to 5, 6, then 7 is here, 8 is here, 9 here, okay, 10 here, 11 here, complicated. Even for us it is complicated, right? Even though levels are given, okay? So the polygon would look like this, which is pretty complicated. What if, okay, what if the levels are not given? So this is the polygon which I want to construct. Okay, and suppose the point is the same set of points, but the levels are not given. Now what we should do? Now, first of all, forget about visually challenged. We are talking about regular persons and normal persons. So maybe you can correct this one. So this is also a polygon, but this is different from this. Obviously, if the levels are not given, there are many ways you can construct the polygon. Reconstruction of polygon is not unique, right? Okay. So as you can see that if I put the levels again, then it must have become wrong. 1 to 3, then 2 should go to 3, but I have connected to 6. This is a different polygon. Okay. So levels are essential. Looks like that, right? If you want to construct the polygon, I will show that levels may not be essential, provided you do some kind of additional work. So let's see how. And that may be useful for visually challenged persons. Okay. So the question is, given an unordered set of points, how do I construct the polygon? Okay. So suppose this is the polygon which I want to construct. And given this set of points, I can do it different way also, but I want this one to construct. And no levels should be given. Then what we should do? Levels will not be given. And I want to reconstruct this one, not this one. How can I do that? Right. So if I want to do that, I need some additional points so that this contour can be defined, right? So one way of doing this, okay, suppose this is my original polygon. If I do this, suppose I put some extra points, So now no levels are given, but still I can reconstruct using the notion of the nearest neighbor kind of thing. Okay, so that means if you put some additional points on the contour of the original polygon, then even if the labels are removed, you can reconstruct the original polygon. Then how many points should be given? How should I minimize it? That is the question. And how should I place the points in? Okay. So vertices are given without ordering, but still the hidden polygon is visually discernible when you add few extra vertices suitably. Let us see how you can generate this. Okay, this is Partha's paper many years ago. Well, okay, so this is based on what is called the Gestalt laws of cognitive psychology. How much time we have? Already many 5 minutes. So one is law of similarity. If you have 2 sets of points, so they look similar. This is law of similarity. And then law of programs, you may think of these are whether segments of arc or see visualize that full circles, all a big sign. Okay, law of proximity, the law of continuity, you know. So if you have this kind of thing, this kind of pattern is visible. So for example, this one, the fork is visible. The law of closure, even if there is a gap here, you can see this pattern. And the law of commonality. I mean, these 2 points, you know, as it belongs to this group. So use this law of proximity and law of continuity in order to solve this problem. Okay, so this is the set of points, the polygon I want to construct, the labels are given. Now suppose, so on the left hand side, I have shown you, I have shown the labels. Now a part of this polygon is shown here. And suppose I want to construct this edge. From 1 to 2, I want to go. Okay, so what I'm going to do, I walk from 1, I find the nearest neighbor, which is 24, and draw a circle with this radius, putting center here. That is with delta radius, I draw a circle, and I put an additional vertex here, which is closer than this nearest neighbor. And then I iterate this process. Okay, so this is called a pseudo vertex. So I look here and look the nearest neighbor here, not the previous one, a new one, and repeat this. Draw a circle here, and put another vertex here within this circle, so that this becomes the nearest neighbor. And repeat this thing. Okay, so once I do this, so these are the pseudo vertices. So what I am going to do now, I will eliminate this, remove these labels. If I start from this, I look into nearest neighbor, and then its nearest neighbor, then its nearest neighbor, and I will come here without the labels. And I do this for all the edges. Okay, so you remove this. So you start here, remove this. So now you can connect this thing. So you can reconstruct this thing. This is the idea. Okay, so no labels are given. So notice that this is useful for visually challenged person. So note in the tablet, if you have this kind of raised dots, so they can have a feeling of continuity. Okay, so they can feel the edge. So the polygon can be describable to visually challenged person like this. Yes. No, but there is a direction of travel there. Next is here. 2 to 3 you have to go, right? So notice that when I go here, so 6 should be very close, right? So there should be closer points, you know. This point should be placed very close to each other. That distance should be less than the distance from 6. Okay, so additional points are there.
The circles are taken of this. Nearest neighbor unique.
Nearest neighbor, I want to make the nearest neighbor of that particular point unique. Yeah, can be estimated, yes. So there is the bound I show you. Yeah. But there is a question of termination also. Okay. So here is an example. So this is the original polygon, and then remove everything, all the labels, vertices are there. So these crosses are extra vertices, pseudo vertices, you know. And then you can reconstruct using the nearest neighbor algorithm. So there are some results, you know. So an algorithm here, so this is the work, you know, one of my students worked here, this manager. Anyway, so there is a result here. I just want to show you this. N is the number of vertices, and suppose this is the vertices plus pseudo vertices, and suppose these are the 2 consecutive edges of the polygon, and these are the pseudo vertices, and so this is the distance from the corner point, which is delta V. So there is a result which says that total number of pseudo vertices or the extra vertices you need to insert so that you can reconstruct the polygon without the presence of the labels. It is given by this expression, where L is the length of the longest edge and delta is the minimum of delta V. That's what it meant. However, there are many open problems here. How to minimize this number, we don't know. Okay, is it NP hard? That you don't know. Well, so this is an example where, this algorithm is useful for, since there is no levels. Okay, so this is for visually, even if somebody is visually challenged, by virtue of the continuity of feeling, you can have the visually challenged person can perceive the shape of the polygon. Right. Start point is there, otherwise. So I'm representing a single polygon perceivable to a blind person, so it was published here. Okay, so as I mentioned that I have one slide that talks about AI tools. Nowadays, a lot of tools are available which gives you voice prompts to visually challenged you. Depending on the environment and situation, use voice prompt. And there are some cameras attached to it which can read any sign or papers or some currency notes, and it's just by voice prompts it recognizes the text and then converts it to speech. Okay, and if necessary, it can convert into Braille's script also. Okay, so this advancing assistive technology is crucial for visually challenged individuals. In fact, teaching geometry to visual challenged is still a very challenging task. So you need new tools to facilitate inclusive education, and this is very important for shape recognition. Is very for visually impaired is very important, and new techniques and corresponding technologies is still lacking. So it's still an open challenge. Thank you very much.
So, if you have a question, please ask, because a lot of things have been discussed. There are many avenues when things work on.
So I end with this is this quote from Helen Keller. Keller, she was blind from infancy, and she wrote a very famous book, The Story of My Life.
Sir, a small question to you. Sir, the electronic devices that are being created, are they for only blind people or visually impaired when we have some operations for normal people also?
Well, no, but normal people, they are not trained in this
Really?
in their early life. Brain requires a lot of training.
Okay, so if the electromagnetic devices can also be created for the people who are being operated and having eye ailments at the later age.
They need some other technology, I guess, because in the past they had vision, I guess.
Like we have pattern recognition. For one, by touching, I can sense this is 1, 2, 3, 4,
No,
or a geometrical figure like circles.
Since they become blind maybe in the later part of their life, they are already familiar with the patterns and so on. All they need is from some kind of picture to text translation.
For like in our later ages, if somebody has some eye ailments, we can also create such devices and help ourselves. Okay. Thank you, sir.
Okay, thank you.
We have one question. If they are somehow taught about the geometry and quantum, etc., they may be also taught about the shapes of the alphabets and numerals.
No, but in real domain, they do not recognize the shape of our alphabet, classical alphabets.
Then help of braille. I take help of teaching the S one or three.
Yeah, possible, But they need this kind of, raised dot tablets, tactile touch, possible.
Because raise is only done by 6 dots and it's an efficient because
I
can always rate A and B and all.
No, but that did not do that because it's already universally accepted, So they nobody wants to change that. You have to redo the entire thing.
One problem. By that time, all the blind people who are there, they won't be able to understand.
Right.
Because Scala TV there are only legacy technology because this was compatible with black and white.
Sir,
Expressed or maybe not exactly, but approximated with the coverage with these few set of finite set of shapes. And so is it possible that the shape and the scale factor, they are somehow encoded and it's easy for them to
Actually, nowadays they are given some physical objects, like just for example, coin. You have a feeling of circle, or balls, feeling of sphere, or cube.
that's how they're taught.
Right.
Text, this is you want to write in a book or something. Can it not be encoded also a small finite set of shapes and some scaling factor?
No, but because they have voice, so you say cube, cube you can write in spells. So, okay.
sir, I have a question.
Hmm.
So as you mentioned about the brain, so I have a question in my mind that is like, sir, as we solve the height and distance solve problems, sir, by drawing the triangular diagrams. So how can the blind people do the same?
No, as I said that this triangle diagram,
Mhm.
you use physical objects,
Ah.
like some sticks or physical objects, and so that they can have a feeling of triangular shape or rectangular shape. You can use physical objects like sticks.
Ah.
That's what they do. Because in braille you cannot express that.
Thank you, sir.
So we thank Professor Bhattacharya for his lovely speech.
Thank you so much, sirs. I would like now request Dr. Bhomik to please felicitate our respected speaker. Sir, please do the honor. Request Dr. Prashanjit Gupta, sir, to please felicitate Dr. Bhomik. Thank you, Dr. Bhattacharya and Dr. Bhomik, for your gracious presence. Thank you, Dr. Bhattacharya, for the wonderful talk. It is truly an enriching experience for all of us. Sir has this incredible ability to explain even complex topics in a very simple manner and engage the audience to the very end. I was fortunate to listen to one of Sir's lecture a few months back, which was organized by ACM Students Chapter, Heritage Institute of Technology. There, Sir had explained how geometry manifests in different fields, such as physics, ancient architecture, and so on. Sir had cited examples that geometry can be applied in different scenarios, like cutting a slice of bread, a pizza, and even in the design of a necklace. Amazing, isn't it? I mean, we are dealing with these kind of objects in our daily life, but we would have never thought of it unless Sir had explained it to us. So we are really grateful to you, Sir. And that day the audience was mesmerized, and today was also no exception. I know all of you will agree to it. So we really look forward to have you in our future events. We will now take a short break. Tea and coffee is arranged in the executive hall outside. I request all of you to assemble in the auditorium within 10 minutes for our next session, where there will be presentation of the track B papers. I also request the presenters of the papers with IDs 102, 13, 7 and 52 to please be prepared. I request all of you to please assemble as soon as possible so that we can start the next session. Welcome back, all of you, to the International Conference on Applied Algorithms 2025, organized by Computer Science and Engineering and allied departments of Heritage Institute of Technology, Kolkata. This session will involve the presentation of 4 papers from Track B, Artificial Intelligence and Machine Learning. Artificial intelligence and machine learning is one of the most evolving topics of computer science, and there is hardly any field where it has not found an application. Hence, rightfully, AI/ML has been kept as one of the tracks in the conference. We are highly privileged to have Professor Dr. Rajat Kumar De as the session chair. Dr. Rajat Kumar De is a professor of Indian Statistical Institute, Kolkata. He obtained his Bachelor of Science Physics Honours, Bachelor of Technology, Computer Science and Engineering from University of Calcutta, and Master of Engineering, Computer Science and Engineering from Jadavpur University in the years 1987, 1991, and 1993, respectively. Dr. De received his PhD degree from the Indian Statistical Institute in 2000. He was also a distinguished postdoctoral fellow of the Whitaker Biomedical Engineering Institute, the Johns Hopkins University, USA, during 2002 to 2003. He visited the Department of Medicine, University of California, San Diego, under Fulbright Nehru Academic and Professional Excellence Fellowship Program, FLEX Award, during 2017 to 2018. Dr. De has authored more than 100 papers published in journals, edited books, and in conference proceedings. His research interest includes modeling biochemical pathways, multi-omics data analysis, pattern recognition, machine learning, deep neural network, and data science. We are really honored to have you here, sir. I request Dr. Rajat Kumar De, sir, to please come up on the stage to chair the session. I once again request the presenters of the papers with IDs 102, 13, 7, and 52 to please be ready. Over to you, sir.
So this is the last session today, track B, artificial intelligence and machine learning of the International Conference of Applied Algorithms 2025. So there are 4 papers, 4 contributory papers. And the first one is Rex's relation extraction using adaptive self-attention by Madhusudan Ghosh, Partha Basu Chaudhuri from Indian Association of Cultivation of Sciences, and Sudeep Noshkar of Jadavpur University. The paper will be presented by Madhusudan Ghosh. One thing I want to remind you, every presenter, so your time is 15 minutes for presentation and 5 minutes for questionnaire.
Am I audible? Good afternoon, everybody. Today I am going to discuss our work. Thus, relation extraction using active self-attention. Myself, Madhusudan Ghosh. The work was done by Dr. Paswas Chaudhary from Indian Association for the Cultivation of Science, Dr. Sudip Kumar Naskar from Janpur University, and this is the table of contents that I am going to discuss today for my discussion. So, coming to the introduction part. So, as you can see from in the slide, that background knowledge is key to intelligent decision making. What do you mean by this? Like, I will try to explain using this following given example. In the below example, we can see that Baksar also is directed by Sandeep Ray. So, being a human being, it is hard to interpret that whether Baksar also is a story, novel, or a movie. And similarly, so who is Sandeep Ray? Sandeep Ray is a director or actor or writer. So it is hard for human being. So for a machine, it is hard to interpret or infer meaningful information from such kind of sentences. So if we have a background knowledge, then we can fetch deeper information using from such kind of sentences. Like background knowledge for, like, let's say we have one graph, that is Baksura also is directed by Sandeep Ray, and Sandeep Ray is child of the great filmmaker Satyajit Ray. So from this information we can infer that Baksura also is a film and Sandeep Ray is a director. Okay, so if we can pass such kind of information to a intelligent system, then then for those system it will be easier to infer or interpret a deeper meaning from such kind of sentences. So this is the fragment of a graph where nodes represent the entities and edges represent the relation between those two entities. So this fragment of bigger graph is called knowledge graph or knowledge base. Okay, and so how we can, next question, how we can build this such kind of knowledge graph or knowledge base from unstructured text. So it is impossible for human being to annotate manually this triplet information, that subject, predicate, and object. To build such kind of age triplet, using this triplet information, we can build the graph. So then the next question is whether we can build an automatic system kind of things. Whether so that we can extract entities at first, and from those pair of entities, whether we can extract relation or classify relation or not, so that we can fetch the structured information to build or populate the existing knowledge graph. So on this motivation, we investigated our work or that relation extraction from unstructured text. So coming to the next part, so this is the example of Google knowledge graph. So in traditional web searching, we knew that when we pass a query, it actually retrieves some document that links, that is sorry, that links, that is these are nothing but documents that actually comes up in Google search. So recently Google popularized one phrase, that things not string. Okay, so previously Google web search engines actually consider both query as strings as well as underlying corpus also as string to fetch relevant information. So after the invention of knowledge graph, Google also tried to include knowledge based information to improve its search engine results. So if we search Google here, so Google will give this kind of harvested head in information, that is structured also. But when the Google was actually founded, who is the CEO? Okay, this kind of information we can get. So this information comes from this knowledge graph. Okay. So, and we know that there are many intelligent systems are there like Amazon Alexa and there are many that Siri. So all these kind of voice assistant system uses their internal knowledge graph to make the conversation. Okay, similarly, Amazon also use its own product knowledge graph to improve its recommendation system. So knowledge graph plays an important role. So, so coming to the relation extraction part, so it can be seen that there are lots of work in relation extraction from unstructured text. So these works can be categorized into two parts. Traditional relation extraction, mostly done using traditional ML-based techniques, and there are neural relation extraction. So the main limitation of these approaches are mostly the most main limitation of these approaches can be categorized into four parts like information loss, long range dependency, lack of long range dependencies, and dependency on external parsers, and limited context understanding. So, so what is that? So to pass an information to an machine learning based model or neural architecture, it is important to tokenize that sentences or use different NLP features by using different NLP parser available in the literature. So, but this type of parsers are not accurate. So if we pass erroneous information to neural architecture or machine learning based system, so it will always generate a lower performance or it will underperform always. So main investigation in this work, like most of the system, and when use graph information to actually extract relation from unstructured text, so um, it actually depends on that dependency parsing information that is actually generated by the external parser. So in counter to that, we actually try to propose our novel Rexas that will try to learn that adjacency representation or dependency parsing information using in training technique from the data itself. Okay, so this is our proposed framework. We call this as Rexas. So this is the let's say this is the sentence that we are going to pass. Okay, so we pass it to the BART pretend module, and BART will inherently actually tokenize these sentences into sub tokens, subword tokens. Where and here we don't require any external tokenizer kind of thing. BART itself will do it. So dependency of tokenizer dependency on external tokenizer that we have mitigated using this way. Similarly, we pass the information to BART and, and then we pass it to the entity indicator module. Because given a sentence and its corresponding entities, we introduce an entity indicator module that is nothing but if we have x1 entity, we will label it as 2 for entity 1 and 3 for entity 2 token, and rest of the tokens we will call it, we are initializing it as 4. And and there are another information that is positional encoding layer. So what is the contribution of positional encoding layer? So when you are considering all the tokens as a bags, so ordering matters because it is important to understand the meaning of a particular sentence where the ordering or occurring of words matters a lot to capture the semantic meaning. So for this reason, we introduce positional encoding layer, and to capture the local contextual dependency, we introduce this VLSTM layer, and later on, and we introduce our novel adaptive self-attention module, which will try to take the output representation from VLSTM layer, and we will try to generate an attention matrix. So we are considering this attention matrix as the adjacency representation, which will be passed to the graph convolution layer to capture the syntactic and global dependency. So BiLSTM is capturing the local dependency and GCN is trying to capture the global dependency. And finally, we try to concatenate all the information and pass it to the fully connected layer to classify the relation. So how we are actually mitigating the existing problems that are available in the traditional relation extraction systems. So introducing self-attention module, we learn the adjacency representation. Okay, and GCN module helps to capture the global dependency and structural, and it introduces structural information also. So makes the dependencies, makes the information more rich. And similarly, as I have already told, that there is no dependency on external parser also. So, and BiLSTM will helps to capture the bidirectional information as well as local contextual information. And so in this way, we train our Icaa module in an end-to-end module. Okay. So coming to the experiment setup. So these are the data sets that we have used for our task. So firstly, I will discuss that all these data sets are distantly supervised data set. So what is distant supervision? So this is the annotation process, that is semi-supervised annotation process. So it is hard to annotate sentences into triplet format. So for that reason, people will takes the help of existing knowledge graph. Let's say we have one sentence and we have two entities in that present in that sentence. Then if those two entities present in a particular knowledge base, then whether say that relation that connect those two entities into a knowledge base, that will be annotated for that particular sentence. So in this way, the distant supervision people actually annotate all the data sets. So the annotated data sets are very much very much noisy. Okay, and we can see from the statistics also. So now the coming to the next slide, that is the research question 1. So whether Icaa can produce state-of-the-art results or not. From the table 2, we can see that Icaa in terms of F1 score, it produces for NYT1 and NYT2 data sets produces a 57.7 F1 score and 59.5. And from the table 3, we can see that Icaa produces 58.0 F1 score. So these are the models that uses external dependency parsing based graph information, graph neural net based framework, and Icaa is outperforming all these framework. And the next question is whether our adaptive self-attention module can replace the dependency parsing, external dependency parser. Okay, so from this table, we can see that Icaa can produce for both NYT1 and NYT2 dataset. It produces 59.5 F1 score and 57.5 F1 score. So it outperforms the module which uses external dependency parser. Okay, and Icaa learn this dependency from data itself. Okay, and this is the adolescent study. So we build initially we use BART along with entity slicer. Then incrementally we increase them by the defined components, and we can see a gradual improvement here. And finally we conclude with Icaa. And another things that we have, so how we can actually control the number of attention head and the GCN layers. Okay, so from this table we can see that if we use number of attention head 4 and the number of GCN layers 2, it produces F1 highest F1 score with 59.5. And so we propose a parser free relation extraction module which can capture this semantic information, and as a future work we can actually extend this work for cross sentence relation extraction, document level relation extraction, in counter to sentence level relation extraction, and we can extend this work for multilingual support. And also we are planning to include that generative AI based technique for this task. So these are the references, and thank you for your attention. Feel free to visit our GitHub repo, and I will happy to take questions.
Okay, so thank you, Madhusudan. So, thank you. So, it's now the time for questionnaire. So if you have any question, anybody? So please.
Go to your research social.
This one?
Yes. Next slide, actually.
This one?
Yes. So this F1 score for your proposed module for NYT one is 0.595 and 0.577, right?
Yeah.
And then the earlier cases, you see 0.529 for the BOT plus 20 slicer. It is slightly better, isn't it? But in your case, it is slightly
So in terms of
inferior.
F1 score, our proposed module is better. So when you are using
So
bar,
what I'm saying is when we compare with NYT 1 and NYT 2,
yeah,
then NYT 2 is worse than NYT 1 in your case, right?
yeah,
Whereas in BART, the first row, the NYT 2 is better compared to NYT 1.
NYT 2 is better in compared to, yeah, yes, this is for the dataset annotation process, because in NYT 1 there are larger number of noise instances is there in compared to NYT 2. So
And I think you should analyze this result, because it appears to me that it is not conforming to whatever was there earlier. In earlier case, NYT 2 was better than NYT 1. In your case, NYT 2 is less than NYT 1. You can do it out. So you just keep it in mind. Okay.
okay.
Any other question? There are these so-called link prediction algorithms. So is this applicable for link prediction where you have partially some links missing?
Yeah, yeah.
So this, you have tried that also?
No, that application part we have not actually
Okay.
So we can apply this
Okay.
because this is all link prediction test.
Okay. Okay. I have one question. How are your Rexes conceptually different from association mining?
Um,
So you understand association mining. So
yeah,
where associations among different entities are extracted. You are also extracting some sort of relation among different entities.
but in association mining, that unstructured information is not there, right? Because we are trying to include this unstructured text. So along with the entity information in association mining, that is missing because some kind of structured information is there in association mining. Here unstructured information will be there. For that reason, it is difficult.
Okay. And the next question is how do you map it to a classification problem?
Because
What are the classes?
yeah, so in the dataset statistics, I have shown that there are 53 classes. Okay, so let's say
53 classes related to what?
means 53 classes related to the knowledge graph, because NYT 1 and NYT 2 was annotated using the knowledge graph of Icaa.
Your objective is relation extraction.
Yeah,
So means what are the classes
yeah,
in this context?
the number of relation classes, let's say, so there in the example I have shown that the relation classes like could be in the knowledge graph will be directed by it is one class. Similarly, child log is one class, location is one class, birthplace is one class. So such classes are defined already in the existing knowledge
Written
graph.
by one class,
Yeah,
child of directed by these are classes.
these are the classes. There are 52 different classes.
Okay.
Yeah, all the years of the class.
Okay. So thank you, Madhusudan. So let us thank you again.
Thank you.
The next contributory paper is HIT Gram a platform for experimenting with n-gram language models by Shiv Ranjani, Dasgupta, Chandan Maiti, Somdeep Mukherjee, Rohan Singh, all from Heritage Institute of Technology, Diptendu Datta from Ornesha Knowledge Technology Private Limited, Kolkata, and Devashish Jana from Heritage Institute of Technology. The paper will be presented by Shivaranjani Dasgupta. So, okay, you know the timing, 15 minutes for presentation and 5 minutes for questioning. And I think you've changed the title a bit, right? Little bit.
Sorry, sir.
You've changed the title of your presentation a bit.
Yes, sir.
Oh, go ahead.
Good evening, everyone. First, I'd like to thank the conference organizers and the conference chair, program chair, for giving me this opportunity to present our paper titled HEADRUM, a lightweight n-gram language modeling platform. It focuses on providing an efficient and scalable text modeling environment platform for resource-constrained environment. Today, I'm presenting this paper on behalf of my co-authors, Chandan Maiti, Somdeep Mukherjee, and Rohan Singh. This paper is based on our final year project under the guidance of Professor Dr. Devashish Jana of CSE Department, Heritage Institute of Technology, and Mr. Diptendu Datta, on Managing Director of Ornisha Knowledge Technologies Private Limited. In this presentation, I will walk you through the motivation behind HEADRUM, the design choices we made, and how we achieved striking balance between efficiency and accuracy. Thank you once again for this opportunity. Let's begin. Now, with increasing work of large language models, the NLP tasks have been revolutionized, like intent classification and text prediction, but they suffer from a lot of challenges. Large language models face challenges with these. First is high computational demand. Large language models require high capacity GPUs. They are internet dependent, and they really create some problems with using them while the users in resource constrained environments. Next is they're inaccessible to users with limited hardware. If the users do not have much memory capacity and they are constrained with limited bandwidth, they may suffer from problems while using it. And next is we are going to see the challenges that are faced by n-gram models. First is data sparsity, that is struggling with word sequences without sufficient training data. If we do not have a specific word or sequence in the training data, the n-gram model may suffer from predicting the next words of those phrases of sequences. And next is fixed context windows. The reliance of n-gram models on fixed context windows restricts their ability to predict more larger context windows or predicting larger sequences after these contexts. And next is handling rare sequences without applying any smoothing technique, like we have applied Lackler smoothing. N-gram models faced with the challenge of predicting rare or unseen words, the words which are absolutely not present in the training data or the corpus. So now we are going to see how
our HITgram approaches these challenges. Despite the dominance of NLP tasks, large language models dominance, they face with the challenges as we have seen in the previous slide, like they face challenges of needing high resource, end resources, memory, and internet connectivity. And Ngram models address these challenges with their computational simplicity, but they suffer from the other challenges as we saw, data sparsity and fixed context windows and zero probability issue. So here there is a really need for a platform that will be providing, that will be addressing all these challenges. So here is Icaa. I present our platform. It is efficient and lightweight. HitGram platform is basically made as on contrary to large language models to be very much efficient in resource constrained environments, as well as it does not need internet connection as compared to other large language model things. Next is handling data sparsity. We have applied Laplace smoothing to address the problem of zero probability issue. And back-of-an interpolation combines different Ngram model lengths like bigram, trigram. It is combining those lengths to predict the words better. Next, we have flexible context modeling. Our platform allows the users to choose bigram or trigram model or four-gram model as they need for their task, whatever is suitable for them. And next is there is no requirement for you, the users, to install a software or any other configuration. You do not need to do that. We provide a single one-click installer that will do all of your work. You just have to install it. Next is the availability of textual data for building models. We allow the users to upload text files or PDF files. You can do whatever. You can upload whatever that is available on the internet. That has to be PDF or text file. So let me introduce HitGram now. This is our user interface. It is a platform. HitGram is a platform specifically designed for experimenting with Ngram models in resource-constrained environments. It focuses on handling small to medium-sized corpora while the resource-constrained environments, and users can upload their corpus file, build Ngram models as they select. It can be bigram, it can be trigram, it can be four-gram. And it is very much ideal for resource constrained environments, and it does not need internet connection. Now we are going to see an overview of Ngram models. So Ngram models predict the nth word in a sequence by analyzing the previous n-1 words in the sequence. We use one of the biggest challenges that are faced by Ngram models are zero probability issue. We have addressed it by using Laplace smoothing to handle the combinations that are very much rare in the corpus data, or that is completely not present, totally not present in the corpus also. And we provide a large range of models for the users to build. We provide unigram, bigram, trigram, four-grams. This makes it a flexible environment. Moving on, we are going to dive into the key features of HitGram. First is tokenization. Our platform HitGram is very much efficient and fast. It processes up to 50,000 tokens per second. And then it has flexible corpus management. User can upload PDF or text file. If you upload a text file, then the platform tokenizes it directly. If you upload a PDF file, the platform will first convert it into a text file. Then it will tokenize the file. Next, we have prediction capabilities. We have used Ngram models that are built first. Then the prediction is made based on those Ngram models. Next comes experimental setup. We have tested our platform by using different corpus sizes and different Ngram values to check the robustness if it performs perfectly in all the environments. So the matrix we have used, our first one is perplexity. Next is the time to load and tokenize the model. And the next one is, next metrics we used is the time to build Ngram model. And we have tested the platform with corpus size from 320 MB to 997 MB. In order to test, it works with larger corpus as well as smaller. Next, let's dive into the experimental results of results. First one is the matrix perplexity. So perplexity is a key metric which is used to evaluate the used to evaluate the effectiveness of language models to predict the next word in a sequence. You can see that we have an experimental result here for, as you can see, as the corpus size decreases, and we have the corpus size, we have bigram and trigram models. You can see as we move from bigram to trigram, the perplexity has decreased. So a lower perplexity depicts better predictive accuracy. That is, it is the lower the perplexity, it is predicting better next words. So you can see that as bigram to trigram, we move from bigram to trigram, the perplexity is increasing. So there is a better next word prediction. Moving on, we have time to build diagram model. So first matrix is load and tokenized time versus corpus time. As the corpus size increases, the graph also increases. That is the time to load and tokenize the text file, that it is also increasing. And next is build time versus corpus time. Means how much time it is taking to build the corpus file with respective text corpus file size. It is also increasing as the increasing size of corpus. Now I'm going to walk you through the workflow of HitGram. First, the user has to upload a text file or PDF file. If you upload a text file, it is going to be tokenized directly. If you upload a PDF file, the platform HitGram will convert it into a text file first. Then it will tokenize. After that, the Ngram model will be built along with Laplace smoothing. Then the user will be able to input the sentence, a part of the sentence that they need to predict the next words for. The n of ngram, the n value for the ngram, like bigram, trigram, fourgram, like that. And they want how many words they want to be predicted. And then if we click on a particular button, which I will show next, the words will be predicted. Let's see. This is the user interface, this one. First, you have to click on upload and build model. Upon clicking on it, you will get a dialog box which will allow you to upload a PDF or text file. In this case, we have taken a PDF file. So the you can see that the PDF file successfully converted to text in 411 milliseconds. Then the size of the, as we have seen that the platform converts the PDF file into text file, then does the work. So the size of the converted text file is also given. And next, tokenization is completed. After that, Ngram model is built from the uploaded corpus file in 434 milliseconds. Then the user has to enter the sentence. Here in this field, we have entered artificial intelligence. Then we have selected the N for Ngram. Here we have selected 3. And the number of words to be predicted. How many numbers after artificial intelligence you want HitGram to predict. So after that, you have to click on this red button called predict next words, and it will give you the next words prediction, that is artificial intelligence is transforming industries. So that was an example for a platform. Next, we are going to dive into what are the advantages of HitGram. And first one is efficiency. HitGram is very much efficient as it is fast, and it can work with a lot of small size corpora to large size corpora. It processes up to 50,000 tokens per second, as we have seen earlier. Next is simplicity. You have already seen that the user interface is pretty simple, and you can learn to use it very fast. And next is adaptability. It works well in all the environment with resource constrained environments. And the main thing is it does not need internet. Once you install it, it won't need any internet connection. It is very much useful for educational purpose or someone who wants to experiment with Ngram models or someone who is doing some research on this topic. It is very much useful. Next, we are going to move on to our future work. Currently, first one is advanced smoothing techniques. Currently, we are providing Laplace smoothing technique. In future, we want to include some more smoothing techniques in order to increase the accuracy of the prediction capacity. Next is multilingual support. Currently, we are providing support with only English language. Next, we would like to include Bengali and some other languages in future. Next is parallel processing. We want to enable parallel processing for larger corpus sizes. After that, we want to allow the users to to select the n of the n-gram dynamically. And next is collaboration features. We want to allow the users to build models together, predict models together, predict next words together. After that, we want to explore the effect of tokenization, such as byte pair tokenization. And next is we want to implement serialization. That is, we want to save our models that are already built into a file, and the users will be able to download those models from those files and use them. So I can conclude that finally with HitDrum is a very much useful, user-friendly, lightweight n-gram modeling platform, and it is ideal for resource-constrained environments. You do not need high-powered GPU or internet connection, something like that. And it is very much user-friendly, and it provides support with trigram, bigram, and other n-gram models. And its improvements are including multilingual support, advanced loading techniques, and scalability. So these are the references we have taken in order to produce HIT gram. Thank you so much, everyone, for the listening.
Thank you, Shubham. So the question is, please.
Okay, so very good work. Very pleased to see your work here. So one question I have, that you mentioned that you want to extend this work to Bengali text also.
Yes, sir.
So the way this English sentences work and the way Bengali grammar works are different.
So completely different. So that's why.
So would you think? So my question is that do you think that the way you have kind of designed the system now, how easy would it be to just take this and retrofit it to a Bengali context where you can predict the next Bengali word? Because the way we think in Bengali is different than the way we think and frame sentences in English.
Yes, sir.
So what are your thoughts on that?
So it is a little bit difficult because, as you said, that Bengali works differently from English. So it will take, I think, more time than it has taken for English. We are currently thinking about
Time
it.
in terms of processing or time in terms of what you want to do?
Sir, what we want to do, it will increase, but processing time we want to maybe we'll be able to decrease it or keep it as English is working.
Thank you very much.
Thank you, sir.
Very good work, Shubham. I can sort of personally identify with the work that you have done. I have a couple of questions, and I apologize, I missed the first part of your presentation. You might have answered.
Sir, do I?
No, just one of the questions is, do you have an experimental result on what is the best value for n?
Sorry, sir.
What are the best results for trigram, 4-gram?
Okay, sir.
Orthogram, what is it giving you better results?
It's a better result.
And the follow-up question is, you did a +1 smoothing, right?
Laplace smoothing.
Are you looking at Jelinek-Mercer smoothing or Dirichlet smoothing? Would that give you better results?
Sir, we have planned to include those smoothing techniques in future. We currently are using Laplace smoothing. And the previous question was n value, sir. So you can see the time to build time is n equals to 1. You can see it actually increases with the increasing corpus size. Yes, sir. So actually the prediction becomes better with increasing n value. It will perform better. Sir, we have actually experimented till 5 like that. N equals to 5. Like
You can check with perplexity.
Yes, sir.
You can check with this perplexity. So whether you can find a bound for n or not. Yes.
Sir, we'll do it in future, sir. I'll
Please.
Type of the sentence consisting of the words. Can sir find out? That is what is a total war before a single particular war.
He's asking that whether in fact you have
She can take the maximum particular sentence in Bengali or English and consider the maximum of the word that is required to make that particular
words
and give the highest value of n. That particular language. Maximum is generated to 1, 2, 3, 4.
Yes.
Not more than that.
Yes.
Any other question?
Can I ask a question? Yeah, so you mentioned that you are looking at alternative smoothing techniques in order to improve the accuracy. What is it accuracy as this is the metrics, perplexity is the metrics, and you say, or do you have a
All the three, complexity and the time to load and tokenize, the time to build. We want to, increase the increase in all the cases.
accuracy of what? What is it?
Prediction accuracy. I mean, how accurately it predicts the next one. That is our one.
When mentioned that currently, is there a value for it?
Sorry,
Is there a current value of accuracy for this model?
the perplexity is showing that the measure of accuracy, how it is affected.
No, I think maybe the question may be this. So we have predicted
Yes, sir.
artificial intelligence is transforming industries.
Yes, sir.
So you are giving artificial intelligence, the system is predicting this.
It's transforming.
Yes, with 3 words, right? So there might be some other sentences
Yes, sir.
starting with artificial intelligence. So the question is, how do you predict? What is the meaning of prediction accuracy in this context?
Sir, actually, we plan to do that accuracy also. I mean, currently we are saying if the sentence is not completely meaningless, it is
Yes.
that is the thing.
Okay, any other question? Okay, let's thanks Shivam. You want to-
Thank you so much for listening. And I want to thank all my co-authors and Devashish sir, Divya sir. Thank you so much for pushing us through our limits and letting us present here. And thank you to the conference and thank you, sir.
Okay, our third paper,
Social evolution of published text and the emergence of artificial intelligence through large language models and the problem of toxicity and bias by Arifa Khan of SRMIST, Sharavan P of SRMIST, and Venkateshan Suki from Sikiwaral Bits. Arifa Khan will present online.
Hi, sir. I'm unable to share my screen. It is disabled. sir.
Not yet. The screen is visible, but not the presentation. Could you please just make your video on so that the audience can know you and see you? Just once.
Yeah.
Okay. Welcome, Arifa, to ICA 2025. Can you hear me?
Yes, sir. Yes.
Okay. So now, now you can start your presentation. So the duration of your presentation is 15 minutes and
Okay, sir.
5 minutes for questionnaire.
Okay, sir. Okay. Good evening to panel members and the distinguished colleagues, all the one and all present over here. Today, I'll be presenting my research on the fascinating journey of how human text evolved into today's artificial intelligence systems, particularly focusing on large language models. Our story spans from early human writing systems to modern AI, revealing how our fundamental need to store and process the information has shaped technological evolution. The key objectives the key objectives of my paper are LLMs are not a substitute for humans. These are not solving the human memory constraints. LLMs excel in managing large scale data retrieval. They serve as tools for augmenting human capabilities but not replacing them. The core human abilities like creativity and decision making remain unmatched by LLMs. This is the first point. The second point is how the GPU evolution, the backbone of LLMs, that is accelerating AI advancements. Today we are here because of the GPU evolution. That is main reason again, apart from the text that is there. GPUs enabled us high speed parallel data processing. The technological advancements in the GPU made LLMs training feasible. Integration of optimized software and hardware has fueled this AI growth. The third objective is LLMs reflect human biases, the inherited flaws of the training data. That is the reason for the human bias that is existing inside the LLMs. Training data is primarily human generated. It is carrying biases. LLM outputs can mirror societal prejudices present in the data. Addressing biases is crucial for developing fair AI systems. Coming to the introduction of my paper, I want to start with an interesting note that human brain, despite having remarkable capabilities, it is significant limitations. There are significant limitations in human memory retention. For example, let us consider none of us can precisely recall what we were doing exactly 1 year ago at this particular time. That is exactly 5 p.m. What we were doing exact 1 year ago. This simple fact illustrates us why humans began developing external memory systems. The limitations drove our ancestors to develop these external memory systems, first through cave paintings, then ideography writings, eventually evolving into phonetic systems developed by phonetic traders. The phoneticians were the ancient maritime traders from the Eastern Mediterranean, now today called as Lebanon. They are credited with developing one of the first widely used phonetic alphabets around 1050 BC. The creation of great libraries to store this human knowledge, that is Babylon, Alexandria, Nalanda, wasn't just about storing books. It was humans' attempt to overcome our biological memory limitation. The information revolution, what is the historical communication technologies, how we got this, how this evolution has been happened, revolution has been happened, the revolution of the information has been happened. The real game changer was the printing press. Suddenly knowledge could not be copied and shared widely. Newspapers emerged in 1620s. Scientific journals began publishing research. By 1665 we had the groundbreaking philosophical transaction, world's first scientific journal, established in 1665 by Henry Oldenburg, the Secretary of the Royal Society of London. It provided us a platform for the scientists to share, publish, and review discoveries systematically. This is the main reason of knowledge created a cascade effect. Newton's revolutionary work, it spread. Leibniz's mathematical innovations, Faraday's breakthrough in electricity. Each step in this revolution wasn't just technological. It was social, changing how humans, it was social. It's changing how humans shared and processed the information. But surely human knowledge started spreading faster and wider than even before. The internet and the Wikipedia took this to a completely new level, putting massive amounts of information at our fingerprints. Later, we are coming to the mathematical foundation. What we are enjoying today, AI, LLMs, everything is what is the background? It has not been started earlier, actually. Think of it way. In 1906, the mathematician named Andrew Markov rules, what we are observing now, come up with this really clever idea. Imagine you're trying to predict what comes next in the text message. That's basically what Andrew Markov started figuring out in 1906. He looked how letters follow each other in the text and kind of like noticing that in English Q is almost always followed by U, or other TH is followed by E or I. He studied by looking at letters in a Russian poem that started these patterns. In the Russian poem is known as Yugin Omegin. Then comes Claude Shannon in 1948. He is called the father of information theory, the concept of entropy, a measure of uncertainty or randomness in the system, what we are now taking into the consideration, helping the information determine minimum amount of data to be needed to represent the information. Think of him as the guy who said that instead of taking all the full words into the consideration, predict what's likely to come next and use to compress our messages. It's similarly to how your phone now suggests that the next word would come when you're typing. Together, because of these two scientists helped change how we think about the language. Before them, people were thinking was just about it was a rule based, grammar based, but they showed the language based all of follow some patterns. The old way was rule based. A sentence must have a subject and then a verb. That was our rule based. Now the new way is it is not like that. It is statistical. That means, for example, a peanut is always 80% followed by butter of the time. This shift was huge because it's actually how modern AI language models work. They don't just follow the strict rules, they learn patterns. How? From millions of examples, just like Marco and Shannon suggested. This changes in thinking laid the groundwork for things like autocomplete on our phone, spell checkers, eventually modern AI chatbots. All these are their amazing works. Next, the phenomenal work is the linguistic debate. Now, this led to an interesting argument years later. One side, Chomsky, a famous linguist who said that actually computers and statistical methods like Markov's approach couldn't really understand language. To prove that, he come up with the word sentence like colorless green ideas sleep furiously. This is a nonsense word actually. This sentence follows all the rules of the English grammar but makes no sense. After all, how can ideas be both colorless and green? And how they sleep furiously? He wanted to show that here, understanding language requires more than just grammar. It requires semantic understanding, the meaning behind the words and this one. Contradicting to this, Peter Norvig, a famous computer scientist, used the statistical methods to analyze Chomsky's sentence. He demonstrated that the statistical models could determine the likelihood of a sentence appearing in English based on the patterns in the data. The key findings of Norvig found that Chomsky's nonsense sentence was 2 lakh times more likely to appear in English than a randomly jumbled version. This often proved us that statistical approaches could distinguish between the structured sentence and gibberish, even if the sentence lacked meaning also. It showed that statistical methods were more effective and nuanced than Chomsky had thought. Now, modern AI models, like large language models, like example GPT, all are built on this idea by using the statistical models to generate coherent human-like text, even without explicitly understanding. The revolution has started and we are in the neural networks. The chapters of teaching the computers how to learn. The first to try was 1961. Frank Rosenfeld created something called perceptron. Imagine it is a most basic calculator of intelligence. It's like a baby's first attempt of learning. It could learn simple things like telling the difference between two circles and squares. This was huge at that time. It was the first machine that could really learn. Next chapter came is Marvin Minsky, who likely a strict teacher who points out the problems actually. He showed that Rosenberg's invention could not handle even slightly complex problem. It's just like the calculator which able to add numbers but got confused if you could ask it to multiply it. Next, the chapter came with the back propagation. It is the breakthrough. Then came a big breakthrough called back propagation. This is teaching the neural networks by giving a feedback. If a student gets a math problem wrong, you show them where they made a mistake so that they can correct it. Back propagation does the same thing. It helps neural networks learn from their mistakes. Next, the evolution. This is where things get interesting. That is neural networks actually. The major three developments: recurrent neural network. Trying to understand a sentence, you need to remember the meaning to make a sense of the end. RNNs were likely giving computers a short-term memory. They could handle tasks like predicting the next word in the sentence. Next came LSTMs. Regular RNNs had a problem. They forget the things quickly. LSTM was like upgrading the computer's memory. Now it could remember important information for a longer periods. That was our development. Think of it being remember the main character in the book while reading through the many chapters. After that one, the amazing Transformers came. This was a game changer, like giving computers the ability to understand the context like humans. Instead of reading the text one word at a time, they look the whole sentence at once. They can understand how each word relates to the another words. This is what powers modern AI like ChatGPT. The basic, it is like watching technology evolve from a basic calculator perceptron to something remember things RNN, better memory, LSTM, and finally something that understand language more like humans, that is transformer. The cool part is that each step built on the previous ones. fixing problems and adding new capabilities, kind of like how phones explained from basic call makers to the smart devices. This evolution is what made possible all the AI tools we use today, from spell checkers to chatbots, and translate, write the questions. Answer the questions and all. The transformer revolution, again here BERT. That is a two-way understanding. Think of the BERT, it is like a super smart reader who can read a sentence both forward and backward. Before BERT, AI used to read from left to right, but BERT can look at a whole sentence at once, like when you look at the picture, how you look at the picture, BERT can tell it's not talking about a money bank. If you give an example of the bank by the river, it can easily explain that it is not the money bank. It is all the words together, but it can say it is a river bank actually. Next, attention mechanism, smart focus of our transformers. Imagine you are in a noisy room, but you can focus on only one conversation. That's what the attention mechanism does for AI. It helps AI focus on the important points of the sentence. GPU power boost. GPUs are like super powerful calculators originally made for the video games actually. Scientists realized these gaming chips could help AI learn faster. It's like upgrading from a bicycle to a rocket ship in terms of a speed actually. This meant AI could process way more information much faster, growing in size and smarts. Early models were like kids knowing a few hundred words. Modern models are having millions of encyclopedias worth of the knowledge. They went from simple tasks like completing
Three
sentences to
minutes
writing
left.
essays. Okay. These are the smart language models which is having the billion million parameters. 170 GPT-1 with 117 million parameters. GPT-3, this is how the revolution has been happened. Now the coming to the important concept, what I'm going to discuss is the inheritance of toxicity and bias. How this inherited bias and toxicity in our data. This is inherited from the training data. AI learns everything from the data it is trained on. And if that data has bias, historical prejudices, or unequal representation, the AI will inherit those biases. There are geographical and demographic prejudices inside that one. There are AI can behave differently for people for different locations. This I observed in a pilot study actually. Now, for example, when I have gone through the Google Ngram data showing the usage of intelligent man versus intelligent woman over time, this data provided some interesting insights that how language and perceptions around gender and intelligence had evolved. How can you say that intelligent man is superior to the intelligent woman? Actually, if you see the distance between these two, it is wider in 1900. Still, this is existing. The usage of intelligent man starts off higher in the early 1900s and remained consistently more common throughout the time period shown. There is a noticeable gap between these two phases I have observed. Later, when I observed, when I did with word embedding models like Glove, Fast Text, and Spacey, when I'm working on this one, I have taken a target word like she, women. When I took the words like she, women, and I had taken the target words like maid, hairdresser, officer, and all. Why? Women and she are more biased towards a maid. The distance, the cosine similarity is showing that women is much similar to maid and hairdresser, whereas a man is a man and he are more having a stronger relation to the
One
supervisor and
minute
soldier.
left.
And then I also observed that the black is associated to a farmer, laborer, and criminal. African is having a strong relationship with the criminal. Caucasian is related to a executive. American leader, executive. What is this? There is bias in the data. And even religion bias is also observed. Islam and jihad frequently associate with the
Hello,
terrorist and
Arifa.
terrorism words. Yes, sir.
You have two minutes remaining.
Okay. These are the 2 minutes. Okay. I'll explain. Final concept, sir. What are the AI limitations? This is the memorization of the training data, the psychopancy, agreeing without critical thinking. The AI might always agree with whatever you say. Memorization, this is where recently Suchir Balaji has also been facing this one. There was an issue of the Suchir Balaji, OpenAI, these leaders also. Logical inconsistencies, hallucinations, context video limitation. Sometimes AI creates information that sounds believable, but it is not correct. The context window limitations, there are certain limitations also. We need to follow some bias mitigation approaches actually. Reinforcement learning from human feedback, input masking and filtering, creating bias neutral training data sets. Expansion is expensive, but it is necessary to remove this bias in the data itself that is existing in the data. We need to remove that. We need to apply certain mitigation strategies on this one. LLMs are not, I want to conclude this as LLMs are not perfect. Large language model makes mistakes and have limitations like technologies. Promising technology with significant challenges. LLMs have great potential, but come with bigger challenges such as handling biases, ensuring accuracy, requires continuous improvement. These models need ongoing updates and learning to stay relevant and effective actually. Developers regularly have to improve LLMs to make them smarter and more accurate. Potential to overcome human cognitive limitations is not there in the LLMs. They can help solve the problems faster than human in some cases, but there is a limitation of cognitive limitations is also there. Ethical considerations are very crucial. It's important to use LLMs very responsibly. Yesterday's news, I have seen that the Tesla's accident actually was guided by Chat GPT, that super stack of Elon Musk and everything. That's developers must consider privacy, bias, and how the AI is used to ensure it benefits everyone. LLMs are powerful tools with rooms for improvement and require thoughtful development and use. This is the main key takeaways from my paper. AI is not just like that. It is an evolution of human communication technologies. The scale brings new capabilities, challenges requires ongoing research and ethical frameworks, potential to augment human intelligence. These are the main areas, key takeaways from my paper. Thank you.
Thank you, Arifa. Let us thank her. Do you have any question? So it seems that there is no question from the audience. Let us thank Arifa again. Okay, Arifa.
Yeah.
Thank you.
Yeah, thank you, sir. Thank you very much.
So the last final presentation in this session, using various machine learning algorithms and XLSTM unit for crop recommendation and disease prediction by Ognish Moitro from Amity International School, Saket. Hello, Ognish. Welcome to ICA. Can you hear me?
Yes, sir.
Okay, so welcome to ICA. So you can have 15 minutes for your presentation and 5 minutes for questionnaire. So you may start your presentation. You please share your presentation and start.
Yeah. Good evening, distinguished guests and my fellow authors. I'm Agnes Moitra from Amity International School, and my research is about using various machine learning algorithms and a XLSTM unit architecture for crop recommendation and disease prediction, crop disease prediction. The results of the paper is summarized as follows. Out of the 41 classifiers from scikit-learn and XGBoost and other gradient boosting methods, I find that CatBoost attained the highest accuracy, AOC, ROC, and F1 score for crop recommendation. And I tested a novel XLSTM unit architecture, which attained the highest accuracy, precision, recall, and F1 score on more than 150K samples for crop disease prediction on 25 plus crop diseases. The objective of this paper was to develop a comprehensive framework for precision agriculture by integrating machine learning models for crop recommendation and crop disease prediction. The motivation was the increasing challenges in agriculture due to climate variability, crop diseases, and resource constraints demand advanced technologies for sustainable food production. And as a result of this, combines machine learning and deep learning techniques to optimize crop selection and improve disease detection accuracy, ensuring better resources utilization and yield. This has a tremendous social impact since it empowers farmers with actionable insights, reduces crop loss due to diseases, and promotes sustainable farming practices to support global food security. Previous research shows that crop recommendation could be done by machine learning for predicting crop suitability based on soil and environmental factors, driving precision agriculture, and nutrient optimization that is incorporating the amount of fertilizers needed can also be used to improve the accuracy, and UAVs and drones could be used in order to remotely detect crop diseases, which was previously done with convolution neural networks. And previous studies have shown that automated methods could be potentially useful in order for to solve this problem. First of all, I use the following dataset from Kaggle in order for the crop recommendation part, and figure 1 depicts the Pearson correlation analysis. We find that there is a significant intercorrelation of the various features, which are nitrogen, phosphorus, and potassium amounts, the temperature, humidity, pH, and the rainfall. And figure 2 depicts the TSNE representation of the entire data set, and this has been grouped by the various crops. The data had quite a lot of outliers as depicted in the TSNE representation, and as a result of this, I used the local outlier factor in order to remove the outliers from the equation. This was done in a method which was similar to how k-nearest neighbors works. We are trying to find clustered groups and remove the outliers based on that. And the local outlier factor or the local reachability density was calculated as follows. In practice, I did this using scikit-learn's library. And moving on to crop disease prediction, I combined the following datasets from Kaggle, and I had around 150K samples with 25 plus disease classes for the following crops as shown here. And talking about the architecture, first I used the unit architecture, which was done to find the segment out the particular places where I could find the disease. As in the entire, I don't need the entire plant per se, but I just wish to look at the images, the flowers, or perhaps the vegetables where the disease would occur. And if for the classification part, I use the novel XLSTM architecture, which builds upon the LSTM architecture and combines it with the insights of the attention architecture. For this, I first went about using the pixel cross entropy loss and the uh, dice loss, which was weighted by their parameters as shown here in order to handle class imbalances. And for optimization, I used the Adam W optimizer over the Adam optimizer for increased stability and generalization. For feature extraction, as I said, I used the unit architecture in order to extract the relevant parts from the entire image, and used the XLSTM architecture along with global average pooling for the final feature aggregation. And at the end, I had a fully connected artificial neural network for making the final prediction using the softmax function. Uh, for the training, I used 100 epochs on a batch size of 16, and this was done using NVIDIA's A100 GPUs on Google Colab. Here is the list of the hyperparameters that I used for this result, for this architecture. And the rationale for using this novel architecture is that uh, combining the spatial features of unit and the temporal integration of XLSTM's temporal modeling, I'm better able to handle the disease in the crop images, and using a weighted loss function was done in order to address the common class imbalances found in the crop disease datasets, which and the AW Adam optimizer was used in order to have a greater generalization, and units encoder decoder structure captures the features at different scale, improving the prediction accuracy across varying disease symptoms. For the crop recommendation part, here's the summary of the top six algorithms which had the highest accuracy. We see a common trend that most of them are ensemble methods, particularly gradient boosters were particularly well here. And all these algorithms were from XGBoost or from their original sources. And this is the feature, the sharp value, which shows the importance of each feature in making the prediction. We see that the amount of phosphorus required had the highest impact, followed by the rainfall, humidity, etc., in order to find which is the appropriate crop to grow in an environment. And moving on to the crop disease recommendation part, we find that the unit XLSTM architecture had the highest accuracy, precision, recall, and F1 score out of all the methods that are tested. In conclusion, this method achieves state-of-the-art results for crop disease prediction and crop recommendation across multiple datasets. This methodology significantly enhances precision agriculture by providing accurate crop selection guidance and early detection, contributing to improve crop yields and sustainable farming practices. Future work could be done in order to incorporate climate forecasting data or environmental data to further enhance the accuracy of crop recommendation and disease prediction, especially in data scarce regions. Leveraging generative techniques, we could also generate uh, synthetic data that could address challenges where data is limited, particularly in order to address the class imbalances. For example, one could potentially use the SMORT method for that. And yeah, that's all for my paper. Thank you.
Thank you, Preet. Any question? So it seems there is no question from the audience. So thank you, Preet, once again. So we are closing the session now. So thank you once again.
Thank you, everyone. Thank you, sir. I would now
Thank you.
request Professor Dr. Shujoy, Associate Professor Dr. Shujoy Shaha, Head of the Department of CSE AIML, to please come up on the stage to felicitate our session chair, Professor Dr. Rajat Kumar Dey. We have come to the end of today's event. On behalf of the organizers of ICAA 2025, I extend a heartfelt vote of thanks to our eminent speakers and the session chairs for their valuable presence. I also thank all of you for actively participating in today's events. I'm sure it was an enriching experience for everyone. The next 2 days of the conference will include more such talks by eminent speakers and presentation of papers which will help us to broaden our ideas and increase our knowledge. We look forward to your continued participation over the following days of the conference. Thank you.